Okay, so today I'm going to give a short description on the wall-tectonic acid and the lipotectonic acid synthesis for gram-positive bacteria. Okay, so first I'm going to describe the gram-positive cell membrane and what it looks like. So these are the surface polymers of gram-positive bacteria. Okay, and they look like this. And these are surface polymers of gram-positive bacteria. And if you recall, just like gram-negative bacteria, which has lipopolysaccharides, gram-positive bacteria has these things called teichoic acid. Okay, and as you all know, that gram-positive bacteria does not have an outer membrane, okay, but it does have peptidoglycan. Okay, it does have very thick peptidoglycan wall, and the gram-negative has a very thin peptidoglycan wall. Okay, but it also has an outer membrane. Okay, so to summarize, gram-positive bacteria has surface polymers in peptidoglycan and its membrane, while the gram-negative bacteria has surface polymers on the outer membrane. Okay, and this is what it looks like for teichoic acids and lipoteichoic acids. So these are the two classes of teichoic acids for gram-positive bacteria. And teichoic acids are important for gram-positive bacteria to have because they serve a purpose to stabilize the cell membrane, okay, and protect the cell membrane from being degraded in this space, this extracellular space, and they also prevent the diffusion of antimicrobials. Okay, so just going to click this. So as you can see, this is the comparison between the gram-positive cell wall and gram-negative cell wall. So teichoic acids look like this. So lipoteichoic acids, actually, if you look at this, these are bendy strings kind of things. These are lipoteichoic acids, and these are bound to the cell membrane. So the cell membrane is just a biphosphate, it's a phospholipid bilayer, okay? And they're bound to that membrane, while the teichoic acids is only bound to the peptidoglycan. Okay, so peptidoglycan actually looks like this. It's a chain of carbohydrates with peptide stems in between. Okay, but these are there are a lot more of these glycan strands than in gram-negative cell wall. Like if you see that gram-negative only has around 2 glycan strands, while gram-positive cell wall has multiples of that, because this has to be thick for the gram-positive cell wall, while the gram-negative bacteria evolved to have an outer membrane, which is composed of lipopolysaccharide and a phospholipid layer. Okay? Alright, so now we're going to talk about the important functions of these teichoic acids. As I said before, it serves to stabilize the cell membrane, it protects the cell wall from degrading, and it prevents diffusion of antimicrobials or antibiotics. Okay, so it plays a very vital role in external aggressors and phage binding, just anything that binds with these gram-positive bacteria. The teichoic acids are going to play a role in it. And now we're going to look at the teichoic acid synthesis process. So this picture is a lot to take in, but we're going to go step by step. So the first step is the synthesis of the lipid carrier. It's called C55PP, or also it's called unidecaprenyl pyrophosphate. And what this is, you can see the little 2- signs here with attached to a stick. That's the UPPCC, C55PP, sorry. And what it's gonna attach to these sugar molecule. Okay, so these are sugar molecules. And that's going to be our second step. So the first step is the synthesis of this lipid by lipid carrier C55PP. The PP stands for phosphates. So these negative molecules are phosphates. Okay. And they're going to attach to these sugar molecules. These are disaccharides. So the darker one is GLCNAC. Okay. And the lighter one is MAN-NAC. Okay. So, and then the third step is going to be the attachment of the phosphates and the glycerol molecules. So these rectangulars are glycerols and the negative signs are phosphates. And these are repeat units. Okay. And another thing to note here is the disaccharides and the C55PP, all of these steps are highly conserved between species of gram-positive bacteria. So if you, let's say, sequence a random species of gram-positive bacteria, you will likely see the disaccharides and the C55PP on its membrane, like most of the time. But the amount of these glycerol and phosphate linked sequences, that varies between species. So that's a variable. So we can look at that and determine what kind of species it is by potentially just looking at the repeat units and how many of these glycerol phosphate groups are there. Okay. And after these are all added, okay, it's going to be flipped into the outer leaflet of the membrane by this TAR-G, TAR-H complex, or TG-TH complex for short, using ATP hydrolysis. So it doesn't show us here, but you need to use ATP to flip this into the outer leaflet of the membrane. Okay, and once it's done that, the extracellular enzymes, which is in here, extracellular enzymes are going to come in and cleave that from the C55PP, the lipid carrier, and attach this thing, the mature teichoic acid, to the peptidoglycan. Okay. And this is we're going to talk about the lipoteichoic acid synthesis. So it's very similar to the teichoic acid synthesis, except that it starts off by adding 2 glucose, UDP glucose molecules to the diacyl diacylglycerol molecule. Okay, so that's going to become a GLC. It just stands for glucose, so it's 2 glucose molecules attached to a diacylglycerol molecule, and that's going to be in the inner leaflet of the membrane first, and then it's going to be flipped by the LTA protein to the outer leaflet of the membrane, and then LTAS protein is going to polymerize the glycerol 1-phosphate chain onto the 2-glucose DAG molecule here, and that's gonna be repeated until it reaches the desired length, and then it's gonna go through a process where this is gonna be cleaved, and this is not cleaved, sorry. This is not going to be cleaved because it's going to be remain bound to the membrane. Okay. And that's the difference between the teichoic acid and lipoteichoic acid.